Well, hello. We're going to go through some of the definitions of acids and bases. These are somewhat formal and are important to answer on a test, but overall, this is not a major idea that we're going through these definitions. So, according to the definitions of acids and bases, and there are different versions, the original version of an acid was the Arrhenius definition. And for an acid, it would be something that produced a hydrogen ion in water. A base would then release or produce a hydroxide ion in water. This is the classic definition of an acid. Acids produce protons, bases produce hydroxide ions. A more formal definition said an acid is a substance that produces the hydronium ion when dissolved in water. Now, I made a small bullseye here. That's the most specific definition for the Arrhenius definition of an acid. As we expand it, now we're going to have a broader definition of an acid and a broader definition of a base. And this is called the Bronsted Lowry definition. In the Bronsted Lowry definition, the acid is fundamentally the same. An acid is a proton donor and it donates a hydrogen ion. It can have other ions in solution, but it must have a proton. Where they differ is the definition of a base. Remember, for the Arrhenius definition of a base, you had to produce a hydroxide ion. But for the Bronsted Lowry definition, a base only needs to accept a proton or get rid of a proton. It does not have to produce a hydroxide. So that's a broader definition. The last definition that we have is very broad, is called the Lewis definition. Now this deals with electron pairs. If you think about when you did electron dot diagrams and valence electrons, that was all, those ideas came from Gilbert Lewis, and he was a Princeton University professor around 1900. And so that's the Lewis definition we're referring to. He dealt with electron pairs. So a Lewis acid is a substance that can accept an electron pair, whereas a base is a substance that can donate or share an electron pair. And we'll go through examples of these to have it make more sense to you. For my class, I really just need you to know the Arrhenius definition and the Bronsted Lowry definition. Knowing the classic definition of an acid, acids donate protons, bases donate hydroxide. That's the classic definition. The Bronsted Lowry definition expands it a little bit more. Just kind of reminding you, you can pause here and read those one more time if you wish. I'm going to kind of continue through on the video. So I've summarized them for you here. The Arrhenius definition: an acid donates a proton, a base, a hydroxide. Now Bronsted and Lowry were actually two different individuals, and so their definition for an acid fundamentally the same, but the difference is for a base, according to Bronsted Lowry, it was a proton acceptor. The acid was a proton donor. And Lewis definition, the Lewis definition has to do with electron pairs. Acids are electron pair acceptors, and bases are electron pair donors. We can look at the definition here. We have the Arrhenius definition: any substance that releases a proton as the only positive ion in solution. So here we have hydrochloric acid. By definition, this will be an Arrhenius acid because in water, it will donate one of its protons over to the water, making a hydronium ion and the chloride ion. So again, here's its definition. Acids form hydronium ions. So here's the HCl donating its proton to water, leaving us the hydronium ion and the chloride ion. So anything that donates a proton is the acid. Here we have the definition of the Arrhenius base. They form hydroxide ions. So here's an example. Ammonia in water makes ammonium hydroxide. That's ammonium plus hydroxide. So here's a base, ammonia. Not shown is an electron pair here. So this is both an Arrhenius base as well as a Lewis base. And the water, in this case, is going to act as an acid because it's donating a proton to the ammonia, so that we end up having ammonium ion, NH4 and an OH1-. some more little information. According to the definition of Arrhenius, a base is a substance whose water solution produces a hydroxide ion as the only negative ion. So let's consider for a moment sodium hydroxide and ammonia and see if these would both be considered to be Arrhenius bases. We know bases are electrolytes and they dissociate. So here's sodium hydroxide. When it dissociates in solution, it will make the sodium ion and hydroxide ion. So that would make it definitely an Arrhenius base. Now, if we look at the dissociation for ammonia, what we have to really remember is ammonia gas gets dissolved in water. It's really ammonium hydroxide. And so what happens is the water is going to provide one of its protons to the ammonia, and you will form the ammonium ion and be left with a hydroxide. So yes, ammonia is also considered an Arrhenius base. It also mentions that bases cause indicators to turn a characteristic color. Now, we've discussed several indicators before: phenolphthalein, bromethymol blue, and litmus. So we could think about what color would litmus paper turn in a base. Excellent. If you said red to blue base, you're correct. Bases can also neutralize acids, and we'll look at some of those neutralization reactions in just a second. If we look at, here's the classic example of an acid, hydrochloric acid, mixed with a base, sodium hydroxide. The ions, the positive ions, switch places, and we're left with a salt, sodium chloride, and water. This is an example of both a double replacement reaction, where water is the driving force, as well as a neutralization reaction. And finally, water solutions of bases, if you were to taste them, they would be bitter. That's a property of bases. And they feel slippery. That's another property that bases possess. So let's discuss neutralization a little bit further. Neutralization is a chemical reaction between an acid and a base in which a salt and water are produced. Now, the salt I'm referring to doesn't have to be sodium chloride. It's any ionic compound, a metal-nonmetal combination of ions. Here's the one we just looked at. Acid, hydrochloric acid, plus base makes salt plus water. Acid because it donates the proton, base because it has an OH to donate, and then we get salt and water. Some neutralization reactions, let's look at another one here. We have, if you recognize this, is sulfuric acid, that's a strong acid, and sodium hydroxide is a base. When the hydrogen and sodium switch places, we'll be left with the salt, sodium sulfate, and water. So in each case, if you have an acid and a base, you will make a salt plus water. This is still a salt as it has the metal ion sodium and the non-metal ion sulfate. That makes it a salt or an ionic compound. We'll go ahead and balance it with coefficients to make sure everybody's happy out there. Let's try another one. This time I have a weak acid. Do you recognize that acid? Good. That's acetic acid. And I'm combining that with a strong base, calcium hydroxide, and we're going to get some switching to occur, but this will be, maybe you remember, a reversible reaction because we have a weak acid. So it will produce some, and we're going to put it here, calcium acetate, and the other product, good. It's going to be water. We always get salt plus water. We'll go ahead and balance that to keep everybody happy, and we'll continue. So neutralization is anytime you have an acid plus a base making salt plus water. We looked at both of these examples, hydrochloric acid and sodium hydroxide making salt and water, and acetic acid and sodium hydroxide making sodium acetate and water. Now, a common misconception is that these salts that we produce are always going to be neutral. And it turns out that's simply not the case. If you have a strong acid and a strong base, the salt that you produce will be neutral. If, though, you have a weak acid and a strong base, or a strong acid and a weak base, your solution will be either acidic or basic. Now, I'll explain briefly, although some of you won't follow what I'm saying at this moment. When you produce sodium acetate, if you looked up at a solubility table, sodium is highly soluble, will dissolve in water, leaving you the acetate ion. This acetate ion will then accept a proton from the water and therefore reduce the amount of acidity in the water, raising the pH, so this salt will act as a base. I'm not going to go through a lot of that in my class. I save those discussions more for AP chemistry. I'm just mentioning here a strong acid, strong base will always produce a neutral salt. A weak acid and a strong base will end up with a basic salt. So neutralization does not always mean you're going to end up at pH 7. Now, if we want to look at salts, here's a bunch of different salts. Sodium chloride you're familiar with. Sodium nitrate, it's called chili saltpeter. Sodium bicarbonate, that would be one that you're going to use if you're doing any cooking, baking soda. And I've listed some other ones here for you. They all have either a metal, nonmetal, or an ion, a positive and negative ion. So they're ionic salts. That's what these things are, ionic compounds. So there's your definition of a salt, an ionic compound that has both a positive and a negative ion in it, other than hydroxide. Now, this isn't really related to this unit, but we'll think about it. Does salt by itself conduct an electric current when it's a solid? And the answer is not very well. If, though, you dissolve the salt in water, it will dissociate, and once you take the solid salt, put it in water, it's ripped apart into ions, and now it conducts an electric current. Well, let's talk a little bit further about salt formation. If we take a strong base like sodium hydroxide and a strong acid like hydrochloric acid, what's going to happen is the H and the OH are going to get together to form water. But that's not what we're interested in. We're interested in the salt. The cation from the salt comes from the base, the sodium, and the anion comes from the acid, the chloride. So in this case, it will produce the salt sodium chloride. Let's look at another example. Let's take sodium hydroxide. Well, I guess it's the same one, just written out for you. Let's try this one, a strong base sodium hydroxide, and this time a weak acid, acetic acid. The same game is going to be played, where the sodium metal is going to form the cation, and the acetate will be the tail or the anion of the salt. So we'll make the salt sodium acetate if you combine sodium hydroxide and acetic acid. The other byproduct, of course, would be H with OH or water. So this is the salt of a strong base and a weak acid. And I've included the equation below for you. Sodium hydroxide plus acetic acid makes sodium acetate plus water. Note, in all of these neutralization reactions, water is always going to be one of the products formed. Let's try another example. This time we have a weak base, ammonia, with a strong acid, sulfuric acid. Now, if you were paying attention earlier, you know that the weak base ammonia is actually ammonium hydroxide. So when this gets together, you're going to make ammonium sulfate. So the salt of the weak base and strong acid, ammonium sulfate, is formed from ammonium hydroxide reacting with sulfuric acid. And I've written the equation below for you as well. Let's take a weak base this time and a weak acid. So we have ammonia and acetic acid. Now, you won't fall for that. If I show you the weak base ammonia, you know I really mean ammonium hydroxide. So when we combine these, the ammonium ion and the acetate ion are going to get together to form the salt ammonium acetate. Water is the other byproduct of this reaction. I hope now you're able to predict the acid-base combination needed to produce any salt, as that could be a question that's asked on your test. So let's practice that skill before we go today. So we were going to play, I call it the blankety blank game, where an acid plus a base makes a salt plus water. So we've got 3 blanks, and I'm going to fill in 1, phosphoric acid. And then if I combine that with, let's say ammonium hydroxide, I want to know what salt is going to be produced. So the first thing we need to do is come up with equations. Phosphoric acid should be H3PO4. Ammonium hydroxide, NH4OH. When these switch places, I hope you can see that the hydrogen and the hydroxide are going to form the water. We're going to be left with ammonium and phosphate. So that when you're left with this, you know the ammonium, the positive cation always comes first, and then the phosphate comes second. Now, I didn't show it, but ammonium is NH4 1+, and phosphate is PO4 3-. So when you do the formation of this, you're going to need to put a subscript 3 here to make everything work out. And the name of this compound is ammonium phosphate. So now we see how we can predict a salt and figure out what acids we need. So let's try another one. Let's assume that I need the salt magnesium nitrate. So we know that if we take an acid plus a base, we'll make salt plus water. So if we look above, notice that the beginning of the salt was the base. So that means the beginning of the salt must be the base, and that means the end of the salt must be the acid. What acid has an NO3? Well, if you said nitric acid, you'd be correct, and that's HNO3. Well, what base do we need then to make this happen? It must be magnesium plus, stick with the classic definition of a base, something that donates an OH. So how about magnesium hydroxide? Magnesium is a 2+ charge, hydroxide is a 1-, so magnesium hydroxide has the formula MgOH2. We'll go ahead and try another one. Let's say we want to make some potassium carbonate. Well, potassium's K with a 1+ charge, carbonate CO3 2-, so that's K2CO3. Again, looking at the pattern, whatever the back end of the salt is going to be the acid. So it's going to end with a CO3. So what acid ends with CO3? If you said carbonic acid, you'd be correct. Now, the base for that is going to be potassium hydroxide, K with the OH. And then we can try yet another one. This time, let's start with an acid. Okay, which acid do we have here? Acetic acid, yes. And what base? Good, aluminum hydroxide. Now, remember what we're doing. The first part and the second part, the hydrogen and the aluminum are going to switch places. So H ends up with OH, that'll be water. And what does aluminum end up with? The acetate ion. Very good. So we're going to end up producing aluminum acetate. Aluminum is a 3+ ion, and the acetate is a 1- polyatomic. So acetic acid plus aluminum hydroxide will produce aluminum acetate in water. Let's try one more. Let's assume I need to make some barium perchlorate. Okay, that's a salt. Now, we know that the metal name on the front is going to make the base. So what base do I need? Barium hydroxide. Good. Now, what acid is going to be made from perchlorate? If you said perchloric acid, good job. Perchloric acid is correct, and it has the formula HClO4. If you wanted chloric acid, it'd be HClO3. If you wanted chlorus, HClO2, and hypochlorous, HClO. We're not going to ask you to know nomenclature here, although I may put together a presentation on that. I won't ask you to name and the nomenclature of acids and bases. Here's our formula for barium hydroxide. Barium is 2+, OH is 1-. When they crisscross, that's the formula. And barium perchlorate, if barium is 2+, and chlorate is 1 minus BaClO4 2 plus water. I hope this makes sense. I hope you understand how acids and bases now produce salt and water. I think that's probably where we're going to stop here for today. There's a definition of the Bronsted Lowry acid and base. Remember, acids for Bronsted Lowry donate protons and bases accept protons. So if we're looking at this case here, the acid is the hydrochloric acid. It's donating a proton to the water. The water in this case is acting as a Bronsted Lowry base because it's accepting a proton from the water. This then forms an acid plus base. We have this salt, ammonium, the hydronium, chloride salt. This is what's being produced. All right, we can watch that happen here. Here's the ammonia. It's going to donate a proton. And here's the water. And it's going to accept a proton. Let's see if that's what happens. Now, I could have said that wrong, and I think I did, because now that I'm looking at it, we're identifying ammonia as a base. So what do bases do? They accept protons. And so the water is going to be an acid. It's going to donate a proton. So there it goes. The water donates its proton to the ammonia. The ammonia accepts the hydrogen ion plus the positive charge. What that means we're going to produce is the ion ammonium and hydroxide. So in this case, water is acting as an acid. If I go back to the previous example, water was acting as a base because it was going to accept a proton from the hydrogen. So water is a special substance called an amphoteric material, which means it can act as an acid or a base. Let's see if there's anything else on here we need to look at. I think that's probably it. We're going to go ahead and hit